Hey, College Math, welcome back. Here is section 3.5. We're going to be talking about conditional probabilities in this section, okay? So our objectives are to identify scenarios in which a conditional probability is needed, and comparing that to kind of what we've been doing so far with probability. And then we're going to calculate some conditional probabilities of single events as well as of sequences of events, okay? So first, let's talk about what is a conditional probability. Well, it pretty much is the probability that an event will occur. So conditional probability is the probability that an event will occur given, and that's going to be kind of a key word in this section, given some other event has already occurred, right? And so we're going to talk, there's kind of a huge focus on independent versus dependent events in this section, right? Because we kind of talked about, if you remember what independent versus dependent means, two events are independent if the probability, or if one event occurring does not affect the probability of another. And so we're actually going to look at a lot of dependent events. We're going to see kind of how some events influence others, or knowing some information influences kind of the overall probability, okay? So let's start with the first example. Suppose your friend draws one card from a shuffle deck and you're trying to guess the card, okay? So this first one, A, what is the probability that the card is a heart if your friend gives you a clue that it is red, okay? And so here's kind of the given statement, so here. So another way we can phrase this is, what is the probability that the card is a heart given that it is red, okay? That's kind of another way to phrase this statement right here that we underlined. All right, these are kind of the same way to say it. So the way we're going to notate this is we're going to say probability of, and actually we're going to write this on the side. So, well, not on the side, but above right here. We're going to say the probability of some event B given A has happened. Okay, so B given A, we're going to notate that by saying P of B, and we're going to use this vertical bar A. Okay, so that's the notation for this kind of stuff. So here what I'm trying to find is the probability of it being a heart given that my card is already red. Okay, and we can also, if that kind of confuses you, you can also write out heart given, we can put a comma here if that helps a little bit too, given red, okay? So we know that our card is red, all right? And if you think about the deck of cards, we have 26 red and 26 black, okay? So that means if we already know our card is red, we're not gonna worry about any of the black cards anymore. We're not gonna even care about those, because why would we guess any of those if we already know that it's red, right? So that's gonna change our total number of outcomes, right? So let me pick a different color here. So this statement right here tells us that our total is not 52 anymore. That's not our denominator anymore. It's actually going to be 26 because we have 26 red cards. Okay, so our denominator is 26 now because it's given, we know it's red. And now out of those 26 cards, how many of them are a heart? Okay, I didn't get rid of any hearts because the heart is a red card, so we're good. There's still 13, right? So we still have 13 hearts. And so that's going to be our numerator because that's the number of cards. Those are the options that we want. Those are our desired outcomes. And so this is our new probability, okay? And kind of look at that and compare it to what the probability of just a heart is, right? That would just be 13 out of 52. But now that we're given this information right here, that narrows down our choices. We don't have to worry about 26 of those choices, okay? So our new probability is 13 out of 26, okay? And so these two events, these two concepts would be dependent on each other, right? Because, you know, the probability of heart was just 13 out of 52. And I'll erase this right here, that way it's not confusing. The probability of getting a heart was just, the denominator was 52. But now that I have heart given red, it's 13 out of 26. That's an example of two dependent events because the probability of heart changes when red happens, okay? Let's take a look at the next one. What is the probability that it is a heart if your friend gives you a clue that it is black, okay? So same kind of idea here. This is our given statement. So if your friend gives you a clue that it is black, that's our, so given that it is black. Okay, so another way we write that is probability of heart. We still want to know the probability of getting a heart, but now given that our card is black to begin with. Okay, so heart, this top part that I'm writing here, you don't have to write this, but you can write this if it makes more sense to you, as opposed to this vertical bar. Okay. So now it's black. So our denominator changes to 26 because again, there's only 26 black cards, right? And now out of those 26 black cards, how many do we have are hearts? Hopefully you're thinking 0, okay? Because this is because there are no black hearts in the deck, right? You can kind of look back at those pictures that we have in our previous practices, and you'll see that there are no, like all the hearts are red, okay? And so it doesn't always just change the denominator, it also might change the numerator, okay? Because we don't have any black heart cards, okay? This numerator still has to kind of go with the denominator. Okay, so always kind of think about that given statement. It affects the entirety of the probability. Okay, so this is equal to 0. Okay, last one for this example. What is the probability that it is a king if your friend tells you that it is a spade? Okay, so this one, probability of king. Why hasn't this gone away yet? Go away, thank you. Probability of king given spade. Okay. So now let's think about this one. And so let's think, how many spades do we have in the deck? And actually, I should have put this in here to begin with. I'm going to grab the picture of the deck of cards so we can both understand it at the same time. Okay, there we go. So here's our deck of cards, and let's kind of go back to 1B really quick. So notice, here are all my black cards, this top first 2 rows. Notice how none of them are hearts. Okay, so that's why we got 0 out of 26, because now that it's just black cards that we're considering, there's the 26, and then out of these 26, none of them are hearts. So now let's think about this last one. What is the probability that it is a king if your friend tells you that it is a spade? So now I only care about the spades, okay? And so how many of those do we have? We have 13. And so that's going to be our denominator, okay? 13, because that is the number of spades. So most often the given statement, the one that comes after given, so like here where it says if your friend tells you it is a spade, remember we can rewrite that as given that it is a spade. That's going to change the denominator most often. There are times where it won't change it because it didn't really affect it, but most often it's going to have the control over the denominator, okay? So 13 is our new denominator instead of 52. And how many of these spades are kings? Okay, notice how we typically have 4, okay? But in the spade section, there's only 1 king. Okay, so there's only a 1 out of 13 chance that our card is a king if it's already a spade. Okay, because now that we know it's a spade, we only have to, there's only one option for it to be a king, which is the king of spades, right? And so our new probability is 1 out of 13. Okay, so that's when this is what we do when we are dealing with just one single card or one single thing. Now what happens when we do 2 things in a row, when we do a sequence of events, okay? So suppose that you draw twice from a shuffle deck of cards. What is the probability that the second is a heart given that the first card was black and you returned it, okay? So the important thing to note here is that even though this is a sequence of events, even though I'm doing one thing right after the other, this is still the one thing that we care about, the probability that we care about, okay? I don't really care too much about the probability of the first and the second. Here, this is asking, what is the probability that the second card is a heart? So I'm still only gonna have one probability. I'm not gonna multiply here because we only care about one card. So only care about this card. Don't need multiplication, okay? Because here I'm not asking what are the chances that this is going to happen and then this is going to happen. What are the chances of these two things happening one after another? I'm only asking you about, okay, what's the chances that this is going to happen if something else already happened, okay? So probability P of, second is a heart. So second is heart, given first is black. Okay, but the thing you have to pay attention to here is that we returned it. Okay, so if I put it back, my total is still out of 52 cards. I didn't take anything away. So that actually didn't really do anything. The chances of this happening is still the same as just getting a heart on the first turn. So 13 hearts out of 52. And so this is because first card was returned. What is going on? Return. There we go. Okay, because the first card was returned, this is just the same thing as the probability of just getting a heart. And so those two things would be considered independent. Okay, these two events are independent. Getting a first card being black and then a second card being heart. Okay, one after another. Because of the fact that I returned it. Now let's look at the next one. What is the probability that the second card is a heart, given that the first card was black and you held on to it? Okay, so now that I'm holding on to it, this becomes different. Okay, second is a heart. What are the chances that my second card is a heart, given that the first one is black? Well, I can't spell. There we go, black. And we held on to it. So now this becomes 13 out of 51. Okay, so here's kind of an example where the given statement doesn't change my probability because I returned it. But here, since I'm holding on to it, that is an example of dependent events. Okay, I'm keeping it so it changes my overall total. It's 13 out of 51 because kept first card. Okay, hopefully that's making a little more sense to you, all right? So kind of the main takeaway is that given statements will change at least the denominator of what the probability would normally be. Okay, and this is for dependent events. If it's independent, it's not going to change it. Okay, so independent events, we're going to see no change. Okay, let's end with one more example. Suppose that your friend rolls two distinct dice at the same time, and you're trying to guess information about the result. So first one is the probability that you roll a sum of 9 if your friend tells you that at least one of the dice is 5. Okay, so I have two distinct dice here. So we have, or remember what we talked about in class, two distinct dice, you immediately think, okay, 36 total outcomes initially, right? That might change based on the given statement. So given at least one dice is 5, okay? So probability that sum equals 9 given at least one is a 5. Okay, so that means in my pairs, I can have, so some of the outcomes that I could have are 1 and 5, 2 and 5. We're actually just gonna write them all down here. 2 and 5, 3 and 5, 4 and 5, 5 and 5, 6 and 5. And then we have the reverses of almost all of these. We have 5 and 1, 5 and 2, 5 and 3, 5 and 4. We don't have 5 and 5 again, and then 5 and 6. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this changes my denominator to be 11 because these are the ones that my given statement gives me. Given at least one is a 5. So here are my outcomes where one dice gives me a 5. So then my new total is 11 because not all 36 have at least 1 5 in them because I have 1 2, 1 3, 1 4, right? So out of my 11, I'm no longer caring about the 36, okay? You've picked all the ones that you potentially want. So you're no longer looking at the rest of them. Out of these ones that you picked, how many of them are going to give us a sum of 9? Okay, hopefully you're kind of saying to yourself, 2, the 4 and the 5, and the 5 and the 4. Those give us a sum of 9. We can kind of double check to make sure. Yes, those are the only ones. So my answer is 2 out of 11. Okay. Last one. What is the probability that you rolled a sum of 7 if your friend tells you that you rolled doubles? Okay, doubles meaning we have the same number on both die. So our outcomes are 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and then 6 and 6. So then my denominator, well, actually, when we write this out, we have probability that our sum is equal to 7, given that we rolled doubles. Okay, so our new denominator is 6. Out of these options right here, are the ones that we've cherry picked, how many of those give us a sum of 7? Hopefully you are saying 0. So our answer is 0. Okay. Conditional probabilities, main takeaway, we're going to first see if we're keeping all our outcomes, okay? Using the given statement, using the if statement, okay? Using the clue that we're given. Based on the clue, we're gonna change our number of outcomes and then maybe even change the number of maybe even change the numerator, the desired outcomes, based on which outcomes we kept and which ones we threw away, okay? As always, you guys, make sure you're asking questions. Hopefully you are doing okay with this stuff. We're almost done with probability. I know you're not a huge fan of it. We have this one and 3.6 left, okay? Have a good rest of your night, and I will see you in the next one.